Hello, good morning. I hope we can hear ourselves very well. Thank you. So let us continue from where we stopped last week. We had looked at the hypergeometric distribution and gave a question, an exercise that involves the hypergeometric distribution. The Kramer student who was able to memorize 8 questions, and the professor is saying that he will pick 6 questions randomly to select for the exam itself. So in that case, I think there was a mix-up in our explanation there. I want to clarify it now. Capital N is equal to 12. Capital K, that is the number of possible questions that Kramer has memorized, is now equivalent to 8, not 6. K is equal to 8. The number of questions he can memorize, that is K, capital K, is equal to 8. So take note of that. N is the size of the sample. The professor says he will set 6 questions and he will randomly pick them from the 12 that he has given them. So N, small n, is equal to 12, to 6 rather. Small n is equal to 6. So those are the parameters. Then, as a result of the nature of the question, if somebody has memorized 8 questions out of 12 that are possible, that are likely, which 6 of them will come out, then it means that whatever the combination of that 6, whatever 6 that were picked, a minimum of 2, he will be able to answer them. And that is only possible when the 4 that he did not memorize are chosen together with any 2 out of the remaining 8 that he had memorized. So in that case, you can see that x begins from 2. The random variable x takes values 2 up to what? What is the last value that x can take? Put it in the comments quickly. What's the last value x can take in that exercise? No, it is not 12. It is not 8. It is 6. Yes. 6, because those are the size of the sample. The maximum amount of questions will be given is 6. So x varies from 2 to 6. So the lowest value of x is 2, while the highest possible value is equal to 6. So x takes 2, 3, 4, 5, and 6. Those are the values that x will take. And the probabilities will revolve around those numbers. When x is equal to 2, you have a probability, so that you can verify that the sum of all the probabilities from x is equal to 2 to x is equal to 6, it will be equal, the sum will be equal to 1. So we can verify that. So that is just clarification for that. And I may provide you some further explanation on that particular one later on, when I'm able to give you a copy of what I've written down. Now, let us go to multinomial distribution. The multinomial distribution. From the notes that we have earlier given, We are looking at the multinomial distribution now. So if you have those notes, you can be going through them. And it is even advisable that if you can print them out, print the note out so that we can be flowing even when there is no, when it's difficult for me to project the document. So we can be flowing and you'll be checking whatever I say, you check it out to understand what I'm saying. So the multinomial distribution, as the name says, it is an extension of the binomial distribution. For the binomial distribution, you have only two possible outcomes for an experiment or a scenario, a process, success and failure. Now, for the multinomial distribution, there are more than two. From 3 upwards, you have the multinomial distribution. So K can be equal to 3, 4, 5, and 6, and so on. And you have various, when you take a sample of size n, and you are in a situation where you have several possible categories, wherein the observation might fall into, for example, an election that you have 3 candidates, or even 20 candidates. If you have an election, we have 20 candidates contesting, and we know the probability of success, or the election result has been announced, and each candidate, including the winner, has been allocated the number of votes that he got. Now, you have that proportion, which is an estimate of the probability of success for each of those candidates. You have that probability, that's the PI in the multinomial distribution, the probability of success of the ith category or the ith group, PI, P subscript I. That is the probability of success of the ith category or group. Now, the NI, small letter NI, N subscript I, those are the number of observations from the sample that relate to that particular category. So the multinomial distribution is an example of a multivariate probability distribution. There are several variables, K of them, that you are looking at, and you are sampling from a population that it is assumed that the population is large, that even if you are sampling without replacement, it does not alter the probability of success. The PIs are fixed. The PI, that is the probability of success, they are all fixed so that it is not altered in any way as you proceed with the experiment or process. The probability of success remains the same. Now, if that is the case, then we will now have a situation where you have K possible outcomes of the experiment, and each of them having its own allocated probability. Each of those K observations or K categories, they have their own allocated probability. And for them also, you have a situation where the various NIs will be given whenever you have a question on relating to multinomial distribution. All the That is sorry for that. The number of observations that relate to the height category. In some cases, you will have a situation whereby if there are 5 categories, if you have 5 categories, then it is possible that you are given the NIs for 4 of them. Now, the NIs, the sum of them, the sum N1 plus N2 plus N3 up to N4 plus N5, it also is equal to the size of the sample, N, small n. So if you are given K of them and 4 of them, and you have 5, the thing to do is just to subtract that total, subtract the remaining, the sum of all what you have from the total, and you have the balance of the last observation or the last category that was not given. That is the way to go about it, and you can easily do the computation from there. Now the formula for the PMF is the the multinomial distribution. Is it a continuous probability distribution or discrete? The multinomial distribution, is it continuous or discrete? It is a discrete probability distribution because you have discrete values. The random variable takes discrete values. What is the random variable in the case of the multinomial distribution? What is the random variable of interest? What is the random variable of interest in the case of the multinomial distribution? The random variables of interest are the NIs, the number of observations from the height category, of which their sum is the sum of them. When you sum all of them up, is equal to N, the size of the sample. So essentially, that is what the multinomial distribution is all about. We are sampling from a large population in such a way that the probability of success for each category remains the same, even when you are sampling without replacement. So it remains the same, and it's like you are carrying n independent experiments, with each experiment resulting in one of k possible outcomes. That is what the multinomial distribution is all about. N, the total of n repetitions of the experiment, and you have k categories in it, sampling without replacement, but it's a large population so that nothing is affected by the probability remains fixed. So if we're able to get the screen out, I'll project it to you for you to see it. So as I said, the multinomial distribution is applicable when you have several it's like a several binomial distributions. That's what the multinomial is. For each of the variables, k, x1, x2, x3, up to xk, they are all binomial, rather, really, binomial random variables, because you have success or failure for each of them. you can only take two possible dis thing: success if it occurs, or failure if it doesn't occur. So that is the nature of the multinomial distribution. Now, when small n is equal to 1 and the k is equal to 2, the multinomial distribution resolves to what? What will be the distribution if n is equal to 1 and k, the number of categories, the number of classes, is equal to 2? What is the distribution that results from that? Thank you. It is Bernoulli distribution. Bernoulli. It is Bernoulli distribution. Also, if k is equal to 1, what distribution is that? Or rather, n is equal to 1. When n is equal to 1, what distribution is that? N equal to 1. Is there in the notes? Okay, when k is equal to 2, what distribution is that? When k is equal to 2, what distribution will we get from that? When k is equal to 2, you have a binomial distribution, only two categories, a binomial distribution. Yes. Now, when n is equal to 1 and you have several k and you have only one n, what type of distribution is that? It's also there in the notes if you can check it out. No, it's not multinomial. It cannot be multinomial. Well, it's a categorical distribution, really. It's a categorical distribution. You have a single sample, a single observation, but it has several categories that it can fall into. So that's a categorical distribution as it were. So that is clear for that. Now, let us see the some properties of the multinomial distribution. So we have given the probability is n factorial as the PMF of the multinomial distribution is n factorial all over n1 factorial, n2 factorial, up to nk factorial. Now multiply by p1 to power n1, p2 to power n2, up to pk to power nk. That is the formula of the PMF of the multinomial distribution. You multiply the factorials, the factorials, the numerator will just be the factorial for the overall size of the sample, n factorial, small n factorial. You now divide it, the denominator will be small n 1 factorial, n2 factorial, up to nk factorial. That will be the numerator and denominator. Then you now multiply it with p1 to power n1, p2 to power n2, up to pk to power nk. That is the way to go about it. So the first property is the 1 to k, I takes values from 1 to k. X1 is NP1. That is, the expected value of X1 is NP1. Expected value of X2, NP2, 3, and so on up to k, xk. Expected value of xk is NPK. The sum of the summation Ni is equal to N, while summation Pi is equal to what? The sum of all the Pi's is equal to what? The sum of all the probabilities is equal to what? Yes, the sum of all the probabilities is equal to 1. The variance, individual observation, is given by NPI times 1 minus PI, NPI QI, really, where QI is equal to 1 minus PI. You can see that each of them, they are binomial random variables with parameters N, Pi. You know, for the binomial distribution, it has parameters N, the size of the sample, and P, the probability of success, which remains fixed. This is also replicated with the multinomial, but in the case of the multinomial, you have k categories. So you have all meshed together to form a single multinomial random variable. So they are all individually binomial random variables. So the variance is NPQ or NPIQI. When you compare with the binomial, you see that the mean of the binomial is NP, and the variance of the binomial you can see them. So it has also covariance, the covariance between the between two variables, xi and xj. So covariance xi xj is just minus n pi pj. I and j are not equal. That means you are not I is not equal to j really. The variance of a variable is separate, then the covariance is related to its relationship with another variable. So that is the covariance of the multinomial distribution. All the covariances are negative because where you have a fixed size of the sample, n is fixed, of a multinomial vector requires a decrease in another component. Because the n is fixed, for example, if you say n is 10, if you are increasing the number of observations for x1, that means you will be reducing the number of observations for some other variables so that n have 0 as their number of observations. So that is the nature of the multinomial. And the PMF of the multinomial distribution it can be expressed using the gamma function, and it shows that the multinomial distribution is also related or resembles what is called the Dirichlet distribution, which indeed in the theory of Bayesian statistics examples in the notes there. The first example is saying that the first example, you say a fair die is rolled 7 times. Sorry for that mix-up. So we can continue. A fair that is the question. You are now being asked. Uh, First of all, before we proceed, those are clear. When you roll a dice several times, a die already has Sorry for the mix-up, for the break in transmission, please. Now, K is equal to 6. Each outcome has its own probability. Of course, they are all equal, 1/6. In the case of a fair die, they will be different. But in the case of a fair die, you have P1, P2, P3, 1/6. So that so that fair die can you hear me very well, please? Is it clear? Can you hear me? Okay. Can you hear me now? Okay. Let's continue. So the example we are talking about, let's read it now. A fair die is tossed 7 times. Find the probability that the number 1 appears twice and the number 2 appears once. That is the question. Now, this is also an example of how you can navigate using the principles of the binomial multinomial distribution. How many categories are there in this question now? How many categories will there be? How many categories? Put the comment, let's see. How many categories do we have for that question? A fair die is tossed 7 times. Find the probability that the number 1 appears twice and the number 2 appears once. Somebody said 2 categories, is that correct? Somebody said 3 categories, is that correct? Once you put give your reason why it is that number. If it's 2, why is it 2? If it's 3, why is it 3? If it's 3 categories, give your reason why is it 3? And if it's 2 categories, you should also give your reason why it is 3. quickly. Anyone that is not hearing, join audio, join with audio. You may not have joined the class with audio. So somebody should put comments to anybody that does not hear that it should join with audio. Except everybody is not hearing me. So somebody has gotten it correctly and gave a reason for it. The question mentioned 2 categories, but we know that the tossing of a die, there are 6 categories, 6 possible outcomes. So they mentioned 1 and 2. So every other thing, 3, 4, 5, 6, they are grouped together as a category on its own. Because you are not interested in those ones, you can say there is others. So there are 3 categories there. 1 can come up, 2 can come up, and the rest of the numbers will come up. So N1 is equal to what? Let's not waste time. N1 is equal to 2. N1 is equal to 2. N2 is equal to 1. Then the balance of it, 7 minus 3, that is 4. N3 will be equal to 4. So since the problem has for 1 and 2, as stated in the comments, the numbers 3, 4, 5, 6 are lumped together into a single event, and it is called orders. You can call it order or give it any other name. So N1 is 2, N2 1, N3 4. N1 plus N2 plus N3 is equal to 7. P1 is equal to what? P1 is equal to what? P2 is equal to what? And P3 is equal to what? P1 is 1 over 6. P2 is 1 over 6. P3 is just the balance of that. That is 4 over 6. So that the sum of all the probabilities will also be equal to 1. That is how to go about it. So the sum of the probabilities will be equal to 1. So P1, 1 over 6, P2, 1 over 6, P3, 4 over 6. So that the probability of P1, S1 is equal to 1, 2 rather, X2 is equal to 1, and X3 is equal to 4. It's just given by that PMF. N factorial, which is 7 factorial, over N1, N2, N3 factorial, multiplied by the necessary probabilities raised to their corresponding powers. So we are talking about P2, 1, 4. So put in the necessary, incorporate them into the PMF, and you have 0.096 as the probability that 1 will turn up 2 times, 2 will turn up once, and the others, you can be silent about the others. Probability that 1 will turn up once, 2 times rather, 2 will turn up once is equal to 0.096, which is approximately equal to 0.1, 1%, a 10% possibility. Now the covariance of those things, you can easily compute them, and that can be done easily. So let us do the covariance of P1, X1, X2. What will be the covariance of X1, X2? It will be equal to 7 minus 7 times P1 times P2. What will that value be? Minus 7 multiplied by 1 over 6 multiplied by 1 over 6. That is minus 7 over 36. For the other one, P1, the covariance of X1, X3 is equal to minus 7 times 1 over 6 times 4 over 6. That is minus 28 over 36. Likewise, the covariance of X2, X3 is also equal to minus 28 over 36. That is clear enough for that as an example. There is another example that I want us to look at. Now, if you have, I want to read out the question. Is the first question on the exercise. The first question on the exercise, let us work it together and get a solution for it. The first question reads thus: in a recent three-way election held in a large state, candidate A received 20% of the votes, candidate B received 30% of the votes, and candidate C 50% of the votes. If 6 voters are selected randomly, what is the probability that there will be exactly one supporter for candidate A? That is one person that voted for A, 2 that voted for B, and 3 that voted for candidate C in the sample. So that is the question. Now, if we did not mention a large state in that question, this is an example of sampling without replacement. So if we delete a large state from that question, what probability distribution can we make use of to solve this problem? Put it in your comment. What probability distribution can we make use of to solve the particular problem if it were not a large state that the sample was drawn from? It is not binomial, wrong. Binomial is wrong. Bernoulli is also wrong. Let me clarify it more. You are sampling from a population that is not finite. That is finite. A population that is finite. You are sampling from a population that is finite, and you are now sampling without replacement. You have 3 categories, 3 classes that any observation can fall into. 3 categories. So what would be the appropriate probability distribution to use for it? If we were sampling without replacement for a finite population, we having only 2 categories, what probability distribution do we use in such example, in such situation? Yes, you use the hypergeometric, but now we are talking about a situation where you have more than 2 categories and sampling without replacement from a finite population. Which distribution do you make use of in such situation? In order not to waste our time, it is the multivariate hypergeometric distribution, correct? It is the multivariate hypergeometric distribution. That is the situation where, okay, if you have said it earlier, I didn't see it. So that is correct, multivariate hypergeometric distribution. That's the example, but let's get back to what we are talking about. It is a multinomial distribution because we are sampling from a large population. So removing 6 persons out of it will not alter the probability of success for each of those categories. So it remains the same. So then you are now asked that if 6 voters are selected randomly, what is the probability that there will be exactly 1 person that voted for A, 2 for B, and 3 for C? So you can say that N1 is equal to what? N2 is equal to N1, N2, N3 is equal to those things that are stated there in the question. N is equal to 6, first of all. N1 is 1, N2 is 2, N3 is 3. When you sum all of them together, it will give you 6, the size of the sample. P1 is equal to what? P1 is equal to what? Yes, P1 is equal to put the correct, yes, 0.2, put it in the way that is seen there. 0.2, P2 is 0.3, and P3 is 0.5. So that P1 plus P2 plus P3 is equal to 1. You can see it. So that probability, somebody should calculate it for us. Calculate the probability in the question and give me the answer within the next 1 minute. 0.135, correct. 0.135 is the correct answer. So you can see that that's the way to go about computing all those, doing example, calculating things using the multinomial distribution. So we shall be having more exercises to help us to firm up our ability to answer questions like this as we proceed. So that is that for the multinomial distribution. We may come to it later on again. But just take note of the properties that we have given you. You have the mean, the covariance, the variance of each random variable, as well as the MGF. We have also given you the MGF of it. And is how it is related to the Dirichlet distribution, which is it is a conjugate prior of that Dirichlet distribution. The multinomial distribution is also a discrete probability distribution. So let us take note of that. The third exercise listed here is an example of a multinomial distribution. That the students in one college have the following rating system for their professors: excellent, good, fair, and bad. In a recent poll of the students, it was found that they believe that 20% of the professors are excellent, 50% are good, 20% are fair, and 10% are bad. Assuming that 12 professors are randomly selected from the college, you are now saying, what is the probability that you have 6 of them excellent, 4 good, 1 fair, and 1 bad, and so on and so forth. Those are the probabilities that you use to, you first of all get the various probabilities stated and proceed with the NI also, N1, N2, N3, N4, which will be varying as the question also varies. So that is for now, that's enough for the multinomial distribution. Any question before we proceed to the next distribution, gamma distribution? Any question? Put your question in the comments if you have any question. State the question quickly. Somebody say I should repeat the formula. If this is book, something that I've already given you out before now. So go to where you got it from your colleagues or whatsoever. What is the difference between the multinomial distribution and the multivariate hypergeometric distribution? Can anybody answer that question before I answer it? Is there any difference between the multinomial distribution and the multivariate hypergeometric distribution? Somebody said the first one is with replacement, the other one is not is without replacement. That may not be, that's not correct per se, really, or it's not comprehensive. That explanation is not comprehensive. It is correct in a way, but it's not comprehensive. Any other answer to it? The difference between multinomial and multivariate hypergeometric. So they are different. The multinomial distribution, you may be sampling with replacement, you may be sampling without replacement, but it does not affect the probability of success. The PIs are unchanged. The PIs are unchanged because you are sampling from a large population. The population is large enough that when you remove from it, it does not affect the probability of success. That is the main point of the multinomial. Whether you are removing and adding back, or you are just removing. So in essence, actually, the multinomial is like you are sampling with replacement, because even when you remove, the probability of success is unchanged. But when you are talking about the multivariate hypergeometric distribution, you are sampling without replacement from a finite population having k categories. Take note of that. You are sampling without replacement from a finite population with k categories. If it is this ordinary hypergeometric distribution, you are sampling without replacement from a finite population with only 2 categories. So that essentially is the difference between the multinomial and the hypergeometric, multivariate hypergeometric. Likewise, you can still have a difference between the binomial and the hypergeometric in that regard. The binomial is like sampling with replacement or sampling without replacement, but you have a very large population so that the probability of success is unchanged. But for the hypergeometric, you have a finite population so that the probability of success alters, it changes as you proceed with the sample. So in essence, the difference between the multinomial and the multivariate hypergeometric is the nature of the sampling. For the nature of the sampling and the population, the size of the population. For the multinomial, you have a infinite population or a large population and you are sampling, whether with replacement or without replacement, it does not alter the probability of success for all the K categories. But for the multivariate hypergeometric, we are sampling from a finite population, we are sampling without replacements, and the probability of success as you remove members from this, as you draw from that sample, from that population, the probability of success continues to change. That is what brings about the multivariate hypergeometric distribution. I think that is enough for that. Let us now proceed to the gamma distribution. Now, the gamma distribution is a continuous probability distribution. It is from a family of what we call the exponential family of distributions and is given by f of x. The parameters are alpha and beta. And the range of the gamma distribution is from 0 to infinity. The values takes values between 0 and infinity. That is it has two parameters, alpha and beta. Alpha is the shape parameter. It is always greater than 0. It is not negative. And beta is the scale parameter, always greater than 0 also. You can take any value from 0 up. Now, if alpha, which is the shape parameter, if it takes integer values, that is, it takes value from 1, 2, 3, 4, 5, and so on, then that distribution now resolves. It now becomes what we call the Erlang distribution. Erlang is just an example of the gamma distribution, but with the shape parameter alpha taking integer values. So is an example, is also a gamma distribution, but we call it specifically the Erlang distribution. The gamma distribution somebody is saying is not in the material. It is there, the one that the typewritten material that I have given you. Number 6 is on page 8, an 11-page document. Page 8 of it contains gamma distribution. Go and get that one. That is the one that I'm talking about. Erlang is not spelled E-long. It's spelled E-R-L-A-N-G. E-R-L-A-N-G is there. Erlang. It is there, please. Let me read what is written there. When alpha is an integer k, the distribution is called Erlang k. This is the sum of k independent exponentially distributed random variables. It is the sum of k exponentially distributed random variables. We have met this before when we are talking about moment generating functions. If you can go to the first page of this document, or rather the page 3. No, page 4. Or from 3 down to page 4. The last line, that is question number 4 in page 3. You say find the Erlang density f of Sn, of t by convolving f of x, which is the PDF of the exponential distribution, with itself n times. Then the big question is find the MGF of x and use it to find the MGF of xn, x1 plus x2 plus xn. So what is being stated there in question 4 on page 4 of this same notes that we are looking at? For those who were unable to do it, is just telling you that the sum of n exponential random variables that are independent of themselves is what we call an Erlang distribution. So it is Erlang with parameter n. So that is that. Let us go back to what we are talking about, the gamma distribution on page 8. So as I said, alpha is the shape parameter, beta is the scale parameter, and you can represent the PDF as stated in the text. Beta to power alpha all over gamma of alpha. That function is called gamma alpha or gamma function of alpha, and it is defined in the next line. That is the derivative or the integral of x to power alpha minus 1 multiplied by the exponent of minus alpha dx, the integral of that. It is the gamma function. And when alpha is integer, we shall look at that, we'll explain it further. It may not be stated in this note, but let's proceed. So there are 3 different parameterizations that are in common use for the gamma distribution. The first one, you can have a shape parameter k and a scale parameter alpha, theta rather. The second parameterization is that when you have a shape parameter is alpha, which is equal to k, an integer, take note, and a scale parameter beta, which is equal to 1 over theta, which we can now call the rate parameter. Beta can be called the rate parameter. Then you can also have a shape parameter k and a mean parameter mu is equal to k over beta. Now, the distribution is used to model waiting times. For example, you go to the car park, you want to enter the bus, and you spend some minutes waiting before you gain access into the bus. That time that you spent waiting can be modeled as a gamma distribution. If you go to the ATM, you meet a queue there, you spend some time waiting before you gain access to use that ATM. It can also be modeled as a gamma distribution. You go to the supermarket, ShopRite possibly. You have bought what you wanted to buy, and you go to the checkout counter. You have a queue there, and you have to spend some time waiting before you will be served or before you will be attended to. It can also be modeled as a gamma distribution. So, and waiting times, as we know, the smallest possible waiting time that you can have is 0. So if it is more than, it can never be less than 0. You cannot have negative waiting times. You can only have waiting times of 0. And if you have a waiting time of 0, what does that mean? It means that when you come in, you don't have to stay in any queue. The facility is accessible immediately you come in. For example, going to the ATM, when you get there and you do not meet anybody, you will not stand waiting you will not be waiting in the queue. You go directly and use the facility. So that is the smallest possible waiting time. So the range of waiting times is between 0 and infinity, which falls in line with the gamma distribution. So the gamma distribution can be used in such situations. The Erlang, which is a special form of the gamma distribution, also has applications in waiting times, because wherever you have a situation where you have to go through several layers of service, an example will be when you want to check in into a plane, you want to travel out of the country, and you intend to go to the airport to do all the check-in formalities. From the time you step into the airport and go to the place where they will check your documents, check your tickets that you are qualified, and you go to another stage where they will check you and your luggage to certify that you have not taken with you any dangerous weapon or things that are not allowed. Then from that time, you now go and sit down to wait for the final checking formalities, where you will now be checked into the plane to board the plane. Until the time you step foot on the plane and have your seat, you have several stages of that. It can also be looked at as an Erlang distribution, where you assume that each of those stages that you have, if it's 4 stages, if it's 5 stages, and so on, they are independent of themselves, and they are exponentially, the time that you spend in those, within those stages, they are all exponentially distributed. Then when you have that, then you will now have an Erlang. If it's 4 stages, it will be an Erlang 4 distribution. So that is a way of Erlang. It can be used to model situations where you have several stages of service. You wait in one stage, go to the next stage to wait, go to the next stage to wait, and so on. Even a common example, as I've remembered now, when we go for a party and we queue up, in that party, they have a lot of food items lined up with the various persons serving part of it to you. So you go on a queue. In the first point, maybe you have rice. In the second point, you have meat. The third, suya. The fourth, chicken. The fifth, salad, and so on and so forth. If you spend some time after you take rice, you now spend some time, and before you now get the next one, meat, you spend some time, you get the other one, and so on and so forth. It can also be looked at as an example of an Erlang distribution, because you have several stages of the service that you will be rendered until you get to the end of the table, and you now collect your tray filled up with all the necessary things that you need for that party, and go and take your seat. You would have spent an amount of time that is broken into various parts. So it's an example, it could be an example of the Erlang distribution. So that is an example of Erlang. So there are some properties of the gamma distribution. The mean is alpha over beta. That is the mean. And, or depending on the parameterization that we have made use of. The one I'm talking about, alpha over beta, is the one given by what we gave as the PDF, the first equation under gamma distribution. So the mean, which is what we will be using really, the mean is alpha over beta. The variance is alpha over beta squared. The mode is alpha minus 1 over beta. Alpha minus 1 over beta. And in that situation, alpha must be greater than or equal to 1. Then the sorry for that break. Can you hear me? Can you hear me clearly? Okay, please let's continue. The network is fluctuating, so bear with us. I will provide that we'll continue to look at. So the gamma distribution, as I said, has an MGF given by what is stated in number 4, item number 4. That is the MGF. The skewness is 2 over root, and it only depends on the shape parameter, or 2 over alpha. 2 over root alpha if you do not have an Helen distribution, it will be 2 over alpha, and k must be, it goes close. It depends only on the shape parameter alpha of k, and it approaches. Now, if X is a gamma distribution with parameters 1, by putting the values into the MGF that is stated in number 4, you can use the moment function to obtain the gamma distribution that has parameter alpha is equal to 1 and beta is equal to 1 over lambda. If you have that, then it is equivalent to an exponential distribution with lambda. And if X is the gamma of nu over 2, that is alpha is equal to nu over 2, and beta is equal to 2, then it is a chi-square distribution with nu degrees of freedom. Nu is that Greek alphabet that looks like V, but it's not V. It looks like small letter V that is italicized. That is nu. So it has a chi-square distribution with nu degrees of freedom. You can see that the gamma distribution is also related to the chi-square distribution Indeed, the chi-square distribution, the gamma distribution, the normal distribution as well, and several other distributions, they are what we call the exponential family. They are part of what we call exponential families. So they are all exponential type distributions. Yes, number 8 now is what was integral that we have earlier on. The integral that is the formula for gamma alpha. If alpha is equal to k, an integer, then we can have a recursive relationship, and it will be gamma k is equal to k minus 1 times gamma of k minus 1, which when we continue to resolve it, it will finally give us k minus 1 factorial. So gamma k, when k is an integer, is just k minus 1, then you have the factorial. So if k is 5, what is gamma 5? Put the answer in the comments. If k is equal to 5, then gamma 5 is equal to what? Four factorial is equal to what? Resolve it, 24. So gamma 5 is equal to 24. Gamma 4 is equal to what? Gamma 4 is equal to what? Yes, gamma 4 is equal to 12. That is 3 factorial. No, gamma 4 is not. Gamma 4 is equal to 3 factorial. That is equal to 6. Gamma 3 is equal to 2 factorial, which is equal to 2. What is gamma 1? Gamma 1 is equal to what? Somebody said gamma 1 is equal to 0. Is that correct? Is gamma 1 equal to 0? Gamma 1 is not equal to 0. Gamma 1 is 0 factorial. And 0 factorial, as we all know, is equal to 1. 0 factorial is equal to 1. So that is the nature of gamma. So gamma 10 will now be equal to 9 factorial. Gamma 9, 8 factorial, and so on and so forth. That's the way to go about it. That's number 8. Number 9, that if x is gamma k alpha, theta rather, then the random variable 1 over x is distributed as the inverse gamma distribution. So the gamma distribution really has a lot of, it has relationship with several other distributions. It's a general form of several other distributions. And number 10 is saying that if x is a gamma alpha theta and y is a gamma beta theta, that is two gamma distributions with the same scale parameter or rate parameter as the case may be, but different shape parameter, then if x is that and y is that, and they are independently distributed, then the random variable x over x plus y is distributed as a beta random variable with alpha and beta parameters. And finally, we state that the negative binomial distribution is sometimes viewed or considered as the discrete type or discrete analog of the gamma distribution. They behave in similar ways. The negative binomial and the gamma distribution. So they are related in that they behave in similar way. We have the discrete form negative binomial, and the continuous form, the gamma distribution, and several other things like that. So some applications of gamma distribution is the next heading. They said the distribution has been used to model the size of insurance claims, the amount of claims from insurance, and even rainfall. That is aggregate insurance claims and the amount of rainfall accumulated in the reservoir can be modeled using the gamma distribution. It can also be used to look at errors in multi-level Poisson regression models. And this is as a result of the fact that the combination of the Poisson distribution and gamma distribution gives a negative binomial distribution. Then also, the gamma distribution, it also has application in Bayesian statistics, where you have prior distribution, posterior distribution, conjugates, because the gamma distribution is a conjugate prior of the exponential distribution, or the conjugate prior for the exponential distribution. Of course, the gamma is related to the exponential distribution, as we have explained so far. And the sum of k exponential distribution is a gamma distribution as well. The sum of exponential distribution gives you a gamma distribution. Rather, independent exponential distributions, take note of that. The gamma distribution is also used to model survival times in survival analysis, as well as customer waiting times in queuing theory, which is what we want to look at now with an example that we will do together to see what is being now. As I said, the shape parameter of the gamma distribution is alpha, and the scale parameter is beta. Take note of that. Alpha is the shape parameter, beta the scale parameter. Now, let us look at this example. It is known that the time in minutes that a customer spends, this one is not in the note, wait, take note. I'm just, we'll work it together and I will clarify if you have any issue. This one is not in the notes, but I will give you the note later. Where this one is located, I'll pass it through later on. It is known that the time in minutes a customer spends waiting before he can use an ATM at UBA Bank is distributed as a gamma distribution with shape parameter 3 and scale parameter 5. Shape parameter is equal to 3 and scale parameter is equal to 0.5. Now the question is, what is the expected time a customer must wait before using the ATM? The expected time of waiting to use that ATM when you come there. The next question is, what is the variance? What is the variance of that distribution, as well as the standard deviation? Of course, we know the standard deviation is the square root of the variance. Then C, obtain the MGF of the distribution and use it to determine expected value of x cubed. Expected value of x cubed. So the solution is like this. What is alpha equal to here? What are the parameters of the distribution? Alpha is equal to what and beta is equal to what? Yes, alpha is equal to what? Beta equal to what? Alpha is equal to 3 and beta is equal to 0.5. So that the expected value of x is equal to alpha over beta. 3 over 0.5, which is 3 times 2, equal to 6. The expected waiting time is 6 minutes. Is that clear? Is it clear to everybody? 6 minutes, expected waiting time, expected value of x. Okay. Expected value of x is 6 minutes. B, the second question, is the variance of x. Variance of x is equal to alpha over beta squared. Alpha over beta squared, what is from that? Variance. Yes? What is the variance?